discuss about the gold foil experiment or alpha particle scattering experiment. Now, this was done around early 1900s, 1905 or so. At the time, people believed that the plum pudding model to be correct. So in this experiment, what they did was they got a very thin sheet of gold and then placed it in a vacuum and then shot alpha particles at it. The reason why gold was used here is because it's the most malleable natural material, so they could make a really thin sample without breaking. So here you can see a very simplified version of this experiment. Alpha particles were shot at a thin gold foil in a vacuum. Now, what happened to these alpha particles after it went through this gold foil was detected on the other side. To do that, they used a microscope and a zinc sulfide screen, which gave out scintillations or like flashes of light whenever they hit. So there are three things you need to know about the observations and three things you need to know about conclusions. That's usually the exam question you get on this topic. So here are the three observations. Most alpha particles went straight through. Vast majority of alpha particles didn't change the direction, they just went straight through. A small number of alpha particles were deflected by large angles as they passed through the foil. So these are the ones that went kind of close to a nucleus and they kind of deflected. And very few alpha particles bounced back. So that is, if it went straight at a nucleus, then it will repel and it will bounce back. The conclusions of this experiment. Now, because most of the alpha particles went straight through, it was concluded that most of the atom space is empty. It's just empty space. And since a small number of alpha particles were deflected, now at this time they already knew the alpha particles were positively charged and they were able to repel them. So they figured out that the nucleus is positively charged and also it was able to deflect an alpha particle or even send it exactly the opposite way to rebound it. So which means most of the atoms must be concentrated in a tiny nucleus. How did they know it's tiny? Because most alpha particles were not affected, only a very small number of them were affected. So it must be a massive in the sense like high in mass, but small in size and positively charged. So these are the three observations and three conclusions. It's a popular exam question. So D is an estimated value for the radius of the gold nucleus, or to be more precise here, is the maximum possible value of the gold nucleus, the radius of the gold nucleus. Now, as this approaches, what happens is the alpha particle loses kinetic energy to do work against the electric field. So kinetic energy lost by the alpha particle is converted into 1 over 4 pi epsilon naught. Epsilon naught is the permittivity of free space, which is 8.85 times 10 to the power of negative 12 farads per meter, multiplied by charge of an alpha particle times by charge of the gold nucleus divided by the radius. So if you know the kinetic energy of the alpha particle and the charge of an alpha particle, which is 2e, 2 times 1.6 times 10 to the power of negative 19 coulombs. Gold, you have 79 protons here. So that's 79 times the value of E, lowercase e, 4 pi epsilon naught. They are all known. So you can calculate the value of R, which is an estimate for the maximum possible value of the radius of a gold nucleus. Here's a question for you to try. An alpha particle with kinetic energy 6 megaelectron volts is fired at a gold nucleus. Estimate the radius of the nucleus by finding the closest approach of the alpha particle to the nucleus. Relative charge on an alpha particle is +2. Relative charge of a gold nucleus is 79. Take the value of E to be 1.6 times 10 to the power of negative 19 coulombs. give it a try. Now, kinetic energy is equal to 1 over 4 pi epsilon naught Q alpha Q gold divided by R. Now, the kinetic energy is 6 mega electron volt. So 6 and mega is 10 to the power of 6. Electron volt to joules, you need to multiply it by 1.6 times 10 to the power of negative 19. So that energy is equal to 1 over 4 pi epsilon naught is that permittivity of free space. Q alpha, so 2 times the charge on an electron multiplied by 79 multiplied by the charge on an electron divided by R. And R, you can just rearrange it. You can cancel some of these 1.6 times 10 to the power of negative 19 on both sides to just make it easier. So R is equal to 3.8 times 10 to the power of negative 14 meters to two significant figures. Now, there are pros and cons of this method of finding the nuclear radius. So, alpha particle scattering provides a useful estimate for the maximum possible size. So, that's a good thing. The calculations involved in this method are relatively straightforward. We just did one, pretty straightforward. Alpha particles interact primarily with protons in the nucleus rather than with all the nucleons, so make the analysis simpler. So here you can see the disadvantages. The sample must be extremely thin to prevent multiple scattering. The gold you need to take should be really, really thin. All alpha particles in the beam must have the exact same initial kinetic energy. It is difficult to obtain alpha particles that rebound at exactly 180 degrees. To achieve this, a very small and precise collision region is needed. All of these are obstructions that we have in this doing it when you try to do this experiment. The gold nucleus will recoil slightly as the alpha particle approaches, which we kind of tend to ignore in this calculation. Alpha particles are hadrons and are influenced by the strong nuclear force near the nucleus, so which you did not really consider in the previous calculations. Also, alpha particles have a measurable size, unlike electrons, which can be often be treated as point masses. So if in other experiment where we use electron diffraction methods, electrons are relatively small compared to the alpha particles, so that gives you a better value, like more accurate one. And it only gives an upper limit for the nuclear radius. Remember, in the first diagram I mentioned that the gap that I colored in yellow. So there could be the alpha particle could stop before it actually hit the nucleus. It kind of gets close to it. So the radius is just an approximation. So if I draw a diagram, here's an alpha particle, and it might stop near a gold nucleus, and we assume that this is the radius, but really the radius is a bit less than that. This is a little bit extreme, like it's not this it's not this strong. I mean, the alpha particle should really be closer than this, but you get the point. So there is a gap between the actual radius and what we get. So what we get here is an upper limit for the radius of the nucleus.